So up to now, in our lectures, we analyzed the behavior of electronic circuits used for communications with small signals, like gain for small signals, like noise generated by amplifiers at small signals. On the other end of the link, on the transmitting side, we need high power. So efficiency here is a problem. Distortion may also be a problem on the receiving end because new signals are generated, and the link is therefore less useful as it would be without distortion. So today we are going to have a look at distortion, and in distortion in particular thinking about communications. And in communications the main problem is really intermodulation distortion. We're going to see what intermodulation distortion is in this first hour, and we are going to see next hour how to calculate the amount of intermodulation distortion for today. That's for today. So first to see what the intermodulation distortion is, and then to calculate the amount of it. In our next lecture, within 1 week, we are going further to talk about countermeasures for distortion, how to reduce distortion in our circuits, how to calculate distortion in all these cases, and also other problems we meet in communications equipment. So let's start this first hour on what distortion actually is in a power amplifier, inside a power amplifier. So if we look at an amplifier as a black box or green box here, the issue that comes up building transmitters, it's amplifier efficiency. So how much power can we get at the output of the amplifier given power available from a supply? And this is equally important from the smallest transmitters, like a mobile phone that has a limited capacity, a battery with a limited capacity, and it has to generate some power to establish the link with the base station, with the network. As well, on the other side, the highest power broadcast transmitters also have the efficiency there is a problem, because the higher the supply power, the higher the cost of the transmitter, the higher the cooling requirements, and also the same cost of the energy here. At high power, with high power broadcast transmitters, the energy cost here to operate this transmitter is a problem. Talking about efficiency, we have to think about the operating point of the active device used in our amplifier. There are some active devices that we cannot actually adjust the operating point, like a laser amplifier or traveling wave tube for microwaves. But many amplifiers using simple gridded vacuum tubes or many kinds of transistors, semiconductor devices, we can select the operating point maybe to improve the efficiency of this device, of this amplifier. For today, for the first hour, we are only going to talk about Class A amplifiers to keep things as simple as possible. So the same kind of amplifiers we are using for amplifying small signals. The power gain, the expression for the power gain is simple. This is the definition of a power gain, so output power divided by the input power. And in the case of small signal amplifiers, this output power is much smaller than the power taken from the supply. So even the output power that's larger than the input is much smaller than the supply power. If we further drive this amplifier with larger signals, maybe we can get to the point that we have about 50% efficiency. So output power divided by the supply power. This is the efficiency. With some amplifiers, we should also consider, if the gain is not very large of this amplifier, we should also consider here for exact calculations also the input signal power that comes into the amplifier. This is also lost. This is also transformed into heat, or maybe summed up to the output power. There are also amplifiers that actually sum up the input power to the output power being generated. For most of our amplifiers, the efficiency is in the range of 50%. So the power transformed into heat is about equal, the same order of magnitude as the useful signal output power. So this is around 1/2 of the supply power. Of course, the exact efficiency may be quite different from this figure, but this is just as a rough approximation what we are doing. So we are dealing about how to make an efficient amplifier with the highest possible efficiency, with the highest possible output power for a given supply power, and maybe even the drive power at the input of the amplifier. So let's look now at the amplifier saturation more into detail. What happens when I drive the amplifier close to its maximum power it's able to generate? What happens? And with all these graphs here, I'm using a logarithmic scale for the input power and also a logarithmic scale for the output power, and also logarithmic scale on the same vertical scale also for the supply power if we are going to consider the supply power required by our amplifier. What happens with an amplifier? At small signals, the amplifier is linear, so the output power tracks the input power increments in exactly the same way. So this line is at 45 degrees here. 45 degrees here. It's lifted from the baseline 45 degrees line that goes through the origin of my coordinate system by the gain of the amplifier. So the linear gain of the amplifier is simply the distance between these two lines, of course in logarithmic units like dBm or dBW, dBwatts. What happens now with this amplifier as we increase the drive? Of course, there is no amplifier that could produce an infinite amount of output power. This thing also somewhat slows the slope of this line decreases as we increase the input power. While driving the amplifier towards saturation to produce the maximum available output power, we may have different behavior from the amplifier. Most semiconductor amplifiers have a limiting performance. So they behave as limiters. They simply limit the output power when we increase the drive here. This at a certain input power, this line becomes practically horizontal, parallel to the horizontal axis, and we have a constant output power, and we call this power the saturation power of these amplifiers. Unfortunately, this P saturation is difficult to define because we also use many types of amplifiers that follow a different curve. For instance, a laser amplifier as used in optics will continue increasing its output power as we increase the input power. Though it provides no more added power, but still the output power increases with increasing the input power. So with the laser we cannot define a saturation because that point does not exist. We have no point where this line would become here horizontal. On the other hand, in radio communication, in microwaves, we frequently use traveling wave tubes. They are still being used on communication satellites because they are more efficient and they have a longer, maybe they have also a longer life than semiconductor amplifiers. For instance, on the Voyager probes traveling through space now for more than 50 years, the traveling wave amplifiers are still operating on those satellites, so on those space probes. So traveling wave tubes should not be neglected here when longevity is a question. Of course, there is no saturation power for many amplifier types. Also, many amplifier types, yes, they do exhibit a limiting operation, but this curve still has a small slope, so it's really impossible to define the saturation power. So saturation power is something we cannot define for any amplifier, but the 1 dB compression point, that can be defined for just any amplifier, because at some particular point, this curve, whatever shape does it have, if it's still increasing, if it becomes constant, or it even drops down, like corrupting the operation of a traveling wave tube, this curve always departs from the this straight line here by a certain amount of dB. And here we can define the power of 1 dB compression when we have a 1 dB difference from the actual amplifier response to the completely linear response. This P1 dB makes sense. As first, P1 dB is the true available output power from the amplifier. So we can actually get this power. In our lecture today, we will deal with many quantities that have units of power, but we actually never achieve that power. We cannot never achieve it, but they're just calculation units. So P1 dB is a real power and is available with some reasonable amount of distortion, with some small distortion is available. So signals can still be used in this point, even if they carry some information in their envelope, not just in their phase. There is also information carried in the envelope of the signal. This can still be carried through. So if we talk about a Class A amplifier, a Class A amplifier typically achieves, at P1 dB, achieves an efficiency of around 30%. It could do more, but we are further down the curve here if we go up with the efficiency. And this is a typical figure for typical amplifiers. And at minus 1 dB, what does it mean? It means a decrease in the power of 20%. A 20% decrease in power is minus 1 dB difference. Or the voltage, decrease in the voltage is square root of the power, proportional to the square root of the power. The voltage decreases by 10%. So the way, say, distortion is usually defined in audio amplifiers in percent, 10% distortion is still something acceptable. Voice is completely intelligible, can be read quite well with a distortion of 10%. So 10% even with amplitude modulation, amplitude modulated voice is still not a problem for our transmission. So this distortion is still small, compared to what we actually need in our link. Of course, each time we depart from the rectilinear response here, we have distortion. So in all this region, we have no non-linear distortion. We didn't actually say how much distortion. We saw that I said that 10% is perhaps useful for audio amplifiers. P1 dB is usually can be defined for any kind of amplifier. Laser, vacuum tubes, special vacuum tubes like beam velocity modulated tubes like TWT, but can be defined for all amplifiers. Sometimes it's not very practical because this curve departs slowly here, and for a multi-stage amplifiers, we usually select the 3 dB compression, not 1 dB compression like for single stage amplifiers, but 3 dB compression, because multiple stage amplifiers have much more gain available. They can still provide useful power and useful efficiency with some reasonable amount of distortion at 3 dB compression. So 3 dB compression is the value usually used for multi-stage amplifiers. Also, when we use the digital pre-distortion in these amplifiers to actually linearize the amplifier, but 3 dB is still a real true available output power with some reasonable amount of distortion that we can compensate for in a pre-distortion circuit. In all our discussions, we are using further on today and also next week, we are using this kind of graphs, so logarithmic units for power on the input and logarithmic units for the power at the output, and also for the supply power. Let's look now a little bit more at the efficiency of the amplifier. We talked about efficiency here since we said that the battery of our phone has a limited capacity, so we are looking for the best possible efficiency. This efficiency here was defined just for a single output power. But our amplifier is not operating all of the time at that output power, especially if the modulation includes envelope modulation, includes amplitude modulation, then this output power is not constant. What happens with a typical Class A amplifier? A typical Class A amplifier, which is also used for small signals amplifiers are always Class A amplifiers, always have a fixed bias point of the active device, of the transistor or vacuum tube, and therefore their power supply is supply power is usually constant. Of course, the supply power is the largest power here in the graph. This is again the real power, but this is the power actually used by our amplifier, not supplied by our amplifier, but actually used by our amplifier. And in Class A, this power is constant. With a Class A amplifier at reasonable distortion, and reasonable distortion means 1 dB compression, at 1 dB compression, we achieve around 30% efficiency. At small signal, with small signals, we don't care about efficiency. We don't care here. At the input of the receiver, we usually don't care about the power drain of our amplifier. And this at Class A, we see that also a Class A amplifier, we may drive it with different input drives and use it at different output powers up to perhaps P1 dB. We are usually not going up to saturation, just up to P1 dB, because here the distortion is reasonable. And what do we know here about the efficiency? The efficiency is the actual output power that may be less than P1 dB divided by the supply power that is constant in our case. So we could rewrite this as P output divided by P1 dB, and the P1 dB efficiency, this is this figure here, so P1 dB over P supply. We know that efficiency at the 1 dB compression point is around 30%. But again, we have P output over P1 dB. So if we use output powers below P1 dB, the efficiency will actually be worse. The efficiency will decrease as the output power decreases. Exactly proportionally to the output power, the efficiency decreases. And this may give us very, very poor efficiencies. Like in multi-tone transmission, like orthogonal frequency division multiplex, in order to obtain an acceptable error vector magnitude, this is the distortion, yet another unit for distortion used with radio transmitters, the average output power over the P1 dB should be around 1 to 10, else we obtain an error vector magnitude that's way too large. If we put this ratio 1 to 10 in this formula up here, we see that the efficiency, the average efficiency of such an amplifier in an OFDM transmitter is just 3%. And this is the main problem of OFDM transmitters, because OFDM transmitters have a very large peak power and a small average power. So this average is quite small compared to the maximum power we can get, and this still should be a real power. So this P1 dB still should be a real power that's available at the output in the linear region, almost linear region of our amplifier, so that we can get it. So we see that the Class A efficiency may be very low with some kinds of modulations. We have other means to improve the efficiency of the amplifier, but this is just to stress that we are talking about a real problem here. How to get the real world efficiency to some useful value, not produce just heat with our amplifier. So let's now have a look into more detail at the distortion in our amplifier. What happens? What do we meet here when this curve departs here, the straight line, the actual response of the amplifier, what kind of distortion do we have? And we could talk about distortion in time domain when a sinusoidal drive it's clipped with the amplifier at its peaks, so the amplifier behaves as a limiter. It does amplify the signal, but it also clips it at the top. So this is certainly distortion that happens, the kind of distortion we can think of here in saturation. If the amplifier is saturating, we are going to get such a distortion at the output. On the other side, we can also think about distortion in frequency domain. When we provide a spectrum with a certain signal spectrum with a certain bandwidth, so this was just a single frequency signal here, this sine wave we had up here. But here we have a certain bandwidth. We need some bandwidth to actually transmit useful information. So what happens when this signal is amplified? Okay, the power of the signal, the overall power of the signal increases. So the absolute value of the spectrum increases. But we get distortion inside the signal here, this hatched area here. We have distortion inside this bandwidth, and we also have growth here of side bands, unwanted side bands. These are just distortion side bands, and this may cause interference to other users in radio communication or crosstalk in transoceanic fiber optic cable. So this regrowth, this spectrum growth here is quite complex, and if this was easy to define just as the percentage of clipping here in time domain for a sinusoidal drive, in frequency domain that's what we really need. We need to transmit a certain bandwidth here. Here the bandwidth was 0. We have this growth of the spectrum, and this is really difficult to predict. We very seldom in radio communication we define a measure how to get from here to here, because this depends much on the spectrum phase, not just the amplitude spectrum, the phase of the spectrum we give an input. We remove the phase here with the absolute sign. For different phases of the spectrum we have different effects here, so it's very difficult to define measurement technique to define this distortion here. We have signals that do have some bandwidth, but they do not generate any distortion. And these signals are usually signals that are phase modulated, that have no envelope variation, no amplitude modulation. Then we have no signal regrowth. But we have signals where this spectral regrowth is very large. So it's very difficult to now quantify how much distortion is this amplifier causing actually. Is this thing going to be disturbing or not? Can we tolerate this thing in our signals or not? Can this spectrum grow here? And also distortions inside the useful bandwidth of the spectrum. And in order to quantify these things, now this problem is a little bit too complex. We are talking about the spectrum phase here, so there are many different possible spectra that can be generated here. Well, in fact, for some transmitters where this spectrum is defined like well defined like UMTS base stations. For UMTS base stations, we drive this the power amplifier of the signal with the well-defined UMTS signal, and we look at the spectral regrowth here, up here. And this signal is defined, but this is a very uncommon case. Usually we have to find a different way to specify the input signal to actually observe the response of the amplifier, and we are going to look further on at what is going here in this hour. So how to define this thing. So let's see now different cases of distortion. In order to make things the simplest way is to describe an amplifier that has no memory, has no energy storage devices here like resonators or LC tuned circuits. Such an amplifier only has an immediate response, but even an immediate response may be nonlinear. So the response of this amplifier may slowly saturate at high drive powers. At high drive signals, the response saturates here. Also, if the amplifier, of course, may be inverting, if it inverts the polarity of the signal, then we get the dotted curve here. But also the dotted curve has the similar has a similar shape. It's the steepest here with small signals, so here the gain is the largest, and then the gain decreases as we go to larger signals. So this actually explains the curve, the saturation curve of an amplifier, what happens with an amplifier. But unlike this curve here does not actually tell us anything about the distortion, except that we perhaps have at P1 dB we have 10% less voltage, so 10% distortion. But this is very, very inaccurate what we are doing here. So what we want to do here is actually have an accurate description to be able to make some calculations. And for such an amplifier that has nonlinearity but has no memory effects inside, no resonators, no tuned circuits, so no group delay in the amplifier, we can express the amplifier response, of course in voltage, not in power, because power will not tell you anything about distortion into detail, but with the voltage. So with the input voltage, input voltage as a function of time in the time domain, we can calculate the output voltage at any particular time. If the amplifier has no memory, we get an immediate result out of this function, and we can rewrite the amplifier response as a polynomial that has a DC term here, that has a linear gain with alpha 1, that has square distortion, cubic distortion. We actually see cubic distortion over here. And has also higher order distortions up to infinity here. The polynomial may have an infinite number of terms here to actually describe our amplifier. What is true for all known amplifiers? All amplifiers have saturation. So the power here only decreases. There is no amplifier that would increase its power up here. It's only decreasing. If the gain of the amplifier is decreasing, then alpha 1 and alpha 3, the two coefficients of the polynomial, should have different signs. So alpha 1 multiplied by alpha 3 is less than 0. Alpha 1 and alpha 3 should have different signs in order to get saturation. Otherwise, we would get the opposite effect. We will see later on, so next week, we will see how to use circuits that actually, how to build and use circuits that actually have alpha 1 times alpha 3 larger than 0, that can compensate for the saturation distortion. But we will see this next week. So this week we just analyze amplifiers that actually have saturation that power is limited. And let's see what happens if we drive such an amplifier with a sinusoidal drive or with a two-tone drive. With a sinusoidal drive, this is just one sine wave. This is a spectrum that has just one spectral line. What we get from the various terms here in this polynomial, and putting in the sine function here. Okay, alpha 0 does not contain the input voltage, so it's just the bias point, the class A bias point of such an amplifier. Alpha 1 generates the same frequency, the sine of omega 0 t. Alpha 2 is responsible for two effects. Okay, it is responsible for rectification. So all rectifiers should have a quadratic response, and is also responsible for the second harmonic generation. We always get both of them at the same time here. We get the second harmonic coupled to the rectification effect. These two go together because if we develop sine squared of a certain of omega 0 t, if we develop the sine squared into into simpler functions without the square here, we get rectification, so DC, and we get the second harmonic. With the third With the third term, the cubic term, what does the cubic term generate? The cubic term generates generates saturation and saturation, because alpha 1 and alpha 3 have opposite signs. This omega 0 will be actually 180 degrees out of phase with respect to the omega 0 we got here. So this actually causes the reduction of the output power, the saturation effect. So this is the saturation we get out. And the third harmonic is, of course, a function of its own. Again, both of them are connected. If we look at further terms up to the polynomial and rewrite the analyze the trigonometric functions we get out of here using the relationships within trigonometric functions, the alpha 4 gives us rectification that counters the rectification of alpha 2. It generates the second harmonic that actually reduces the second harmonic generated by alpha 2, but the new term here is fourth harmonic. The fifth term is again omega 0 that has the opposite value of this one, so it works against saturation. We had 3 omega that actually starts killing this 3 omega here, and we have the fifth harmonic. With the sixth term we get up to the sixth harmonic. With the seventh term we get up to the seventh harmonic. So the harmonic number is actually proportional, using trigonometric function relationships, is actually proportional to the term we have. So if this polynomial would end up earlier, say just up to the fifth harmonic, up to the fifth power, we could only get the fifth harmonic out of such an amplifier. If we look this in the spectral domain, if we look at the spectrum, what we get at the output of an amplifier that has all these terms. The linear term gives us the amplified signal, and besides the amplified signal we have a DC bias of this amplifier, and we have rectification effects here. We get the second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic. With the single tone drive, the single tone spectrum is quite simple. We only have harmonics, exact multiples of the fundamental frequency we are driving the amplifier here. Here I stopped my my graph here at the fifth term here. I only used the first sixth term from alpha 0 to alpha 5 here. So this here, the response is quite simple. And in radio we are usually dealing with narrowband signals. Narrowband signals means that the bandwidth of the signal is less than 10% of the central frequency. If it's less than 10% of the central frequency, it's rather easy to build filters to filter out just the desired fundamental frequency omega 0. 10% bandwidth compared to the, say, unloaded Q of 100 of simple inductors, wire-wound inductors, this can be made. So such a filter can be made with relatively small insertion loss. We can just filter out the fundamental frequency, and we can remove all unwanted harmonics. And of course the DC will never get radiated, but anyway DC can be stopped by a coupling capacitor. We can completely stop any DC signal in the output. So this should really be at the output just a low pass filter to filter out the harmonics, and some AC coupling with a coupling capacitor to remove out the DC. So this is very simple to remove here. These unwanted terms are quite simple to remove. So it seems that in radio we are able to handle distortion. We have a similar effects also in optics, in optical fibers. In optical fibers, the important bandwidth of a signal is quite limited. Not because of the fiber, because the fiber is quite broadband, but because the nonlinearity in optics is distributed, and with the phase mismatch we can only the only terms that we actually set the output are those close to the input frequency. So it's very difficult to generate the second harmonic, the third harmonic, fourth harmonic, and so on in optics, because we have to deal with phase mismatch, because the nonlinearity in optics is distributed. If we are building a frequency doubler for a laser with a suitable crystal, we usually counter the phase mismatch at the second harmonic. Usually counter this by using the birefringence of the crystal and adjusting the angle of the input ray and the angle of the output ray to enable phase matching. So this is a more difficult subject in optics. So single sinusoidal single tone drive generates a very simple spectrum that's easy to handle in radio communication. But not all things are that easy. In radio, we usually need to transmit useful information. We need some bandwidth. Now, this was very difficult to represent. Because for different phases of the input spectrum, we get different result here. But trying to find the simpler signal to describe a radio signal, and the idea is to use a two-tone drive. A two-tone drive where we drive the amplifier with two tones. These two tones may have different amplitudes. U1 and U2 may be different here, the amplitudes. Okay, alpha 0 again is just the bias point. If you only have alpha 1 in the transfer function, alpha 1 is just amplification, so of both omega 1 and omega 2. This is what we want. The linear gain is usually what we want out of our amplifier. But any amplifier will also have higher order terms, especially if we come close to saturation. And the square term alpha 2 will generate the second harmonic, will generate rectification, will again generate the second harmonic, but it will also generate mixing. So at the output amplifier we see the sum of both input frequencies and the difference of both input frequencies. So this is something new, and we looked at mixing already in our previous lectures when we actually wanted mixing. We want to do mixing for signal processing inside the receivers. Now this mixing may be also a disturbing feature of a power amplifier. This mixing products may cause problems. With the cubic term, the alpha 3, we get saturation. Also here we get saturation, maybe here. And saturation is given by this omega 1 and omega 2. They do generate saturation because of the opposite sign of alpha 3 with respect to alpha 1. Also, this omega 1 and omega 2 will be just of the opposite phase of this omega 1 and omega 2 generated here. So this causes gain decrease, power decrease. We get the third harmonic at both frequencies, and we get third order mixing. So 2 omega 1 plus omega 2, or 2 omega 1 minus omega 2. And so on. You see that we have many different terms here as we increase the power here, the index of the term here. The higher the term, the cubic term already generates many different distortion products here. The alpha 4 has even more products. Alpha 4 is still a term, the fourth term, that we can rewrite down all these terms here. We have DC, we have second harmonic, and square mixing here, that actually all these terms here are out of phase with these terms here. So this actually describes the saturation of the process. But we have also fourth order products like fourth harmonic, and we have fourth order mixing that has many different terms here. You see, it's 3 omega 1 plus omega 2, it's 2 omega 1 plus 2 omega 2, it's omega 1 plus 3 omega 2. So there are many different terms we get, and the fourth alpha 4 is still something. I can write all these terms here on my board here. Alpha 5 already has many different terms. I'm unable to write them. The same for omega 6. I could do the same now, converting the trigonometric functions, the powers of the trigonometric functions, into trigonometric functions of larger arguments. Alpha 6 and alpha 7 also have many terms here. Still, looking at this spectra here, we don't understand much about the problems that are actually going on in our amplifier. And we see this if we plot the spectrum. So omega 1 and omega 2, if they represent a real radio signals, that should be quite close compared to the average value of these frequencies. So omega signal is less than 10%, so these two are quite close together here. We get a very complex spectrum, drawing down now all the higher order products up to the term 5. So I drew here all the products up to the term 5 here. The fifth term, I neglected the higher order terms just because of simplicity here on my drawing. And you see that the spectrum here is very complicated. Trying the same countermeasure as we did with the sinusoidal drive with a single tone spectrum, we can remove some of these components. If this yellow rectangle here is the pass band of our filter, we can see that we remove many of these higher order mixing products. We can remove them here. But there are some mixing products that cannot be removed because they are close, very close to omega 1 and omega 2, especially if we decrease the distance between omega 1 and omega 2. If these two are very close, these mixing products here will go through any passband filter. So a passband filter is not a countermeasure to remove these products. We cannot do that for an arbitrary signal because omega 1 and omega 2 may be extremely close one to another. So what does that mean? That means that these distortion products are somewhat special. They actually happen inside the bandwidth of our useful signal, and that's the reason why they have a very special name. They are called intermodulation products. So these mixing products actually happen inside the bandwidth of our system. That's the reason why they are called intermodulation, and there is no way we could remove them. We can just work with an amplifier with a better linearity, with a smaller alpha 3, but as soon as we have an alpha 3, we have intermodulation distortion. And this intermodulation distortion, actually, because it's caused by alpha 3, is called intermodulation distortion of the third order. We also have with alpha 5, we get fifth order. With alpha 7, we have 7th order. If we looked at the spectrum, so these two are our original two signals. Third order intermodulation distortion is this thing here. Fifth order intermodulation distortion is this thing here. So for narrowband systems, for narrowband amplifiers, we only have odd order intermodulation products. So we have third order, we have fifth order, 7th order, and so on. So if we look now into detail into the intermodulation spectrum, let me explain now this measurement here on this figure here. We have an amplifier that amplifies the useful signal, and it has a total distortion that has all these spectral lines we drew here. And this amplifier is followed by a bandpass filter. A bandpass filter that removes many of these unwanted products here. In the case of a single tone drive, it can remove all distortion. But in the case of a two-tone drive, this filter cannot do miracles. And after this filter, this is what we call intermodulation distortion inside the useful passband of our filter, of our modulation. So inside the useful passband, if the two tones are rather close together, then there is no way to remove them with the filter. So the bandwidth of this filter is actually larger than the difference of the two frequencies, but this is much smaller than the single tone drive or the two tone drive frequencies. And this is just to explain what intermodulation distortion is, and this intermodulation distortion always makes it through all bandpass filter. This is intermodulation distortion is going to corrupt our signal also corrupt the useful signal for our receiver, but also generates some signals outside our useful bandwidth, so the bandwidth used by other users, causing crosstalk to other transmissions, or over radio or over optical fiber. This always happens, and this cannot be removed. So this is the problem here. This is just the diagram that should be used with both this spectrum and this spectrum. So this yellow box here is actually the pass band of our filter we had at the output. Intermodulation distortion is the thing we are going to talk today. Intermodulation distortion is also the thing we are going to look at countermeasures next time with our lecture next week after one week here. So let's look now into detail at the spectrum of intermodulation distortion. The spectrum of intermodulation distortion has many components. So if omega 1 and omega 2 are the two original test tones of the signal spectrum, I have the red lines here, intermodulation distortion of the third order, then I have intermodulation distortion of the fifth order, intermodulation distortion of the second order, this one here and this one here, intermodulation distortion of the ninth order, here and here, intermodulation distortion of the 11th order, here and here, of the 13th order, of the 15th order, and so on. So intermodulation distortion in narrowband systems only causes even order intermodulation. Odd order intermodulation products. So we only get IMD 3, 5, 7, 9, 11, 13, 15. All these products are always spaced by delta omega. If delta omega was the difference between the two original frequencies, they are spaced at delta omega, and this may extend up to infinity if our original polynomial up here had an infinite amount of terms. And this may happen with actually a diode response. A semiconductor diode response is usually an exponential function, and exponential functions have an infinite, when converted into polynomials, have an infinite number of terms. So this actually happens. So our spectrum is now, intermodulation spectrum is actually able to grow here to infinity. Now a real mathematician would start crying here. So with just two tones I covered all the spectrum with distortion, all the available spectrum with distortion, so I made a really bad problem. That's the problem as seen by the mathematician. The mathematician always calculates everything accurately with the polynomial he has. But from the standing point of an engineer, it is not necessarily to kill this intermodulation progress down to zero. It's just, from the engineering point of view, it's just sufficient to have these intermodulation products of sufficiently low amplitude. So if we are able to manage the amplitude of this product, to manage the distortion that is low enough, then we can use such an amplifier. And in fact, next hour we are going to see into detail here how to calculate this spectrum, the magnitudes of these spectral lines exactly. We know the position, we know exactly with delta omega. The actual frequencies are very easy to calculate, but the magnitudes, we have to find the methods how to calculate the magnitudes of this distortion that is happening in our amplifier, and also how to specify the amplifier in terms of distortion. So how to specify the amplifier to have the distortion, keep the distortion low enough for our intended purpose. So next hour we are going to calculate the magnitudes of the various spectral components we have here.